I want to talk to you today about the sizes, shapes, and kinematics of early galaxies with JWST. A lot of the things in this category have already been covered by the three fabulous talks earlier this afternoon. So in general, I will be skipping the things that they talked about and kind of filling in around the edges. Often when we're pushing the boundary of what's possible observationally, in particular towards the highest redshifts, we treat galaxies as point sources, right? We're like, oh, that's cool. We can't resolve it, so we'll just pretend like it's not resolved. It's just a single photometric point. But there's actually an incredibly rich amount of information in spatially resolved properties of galaxies, right? You can learn from the star formation histories of galaxies when things form, but in order to really understand how things form, it's really helpful to get hints from their kinematics, their shapes, their sizes. So it is in that context that I'm going to be talking to you about those things today. And of course, in the context of galaxy formation, we're really kind of at the crux of cosmology, going to larger scales, and star formation going down to smaller scales. And so when we're trying to understand these features of galaxy formation, especially in the early universe, we hope that it will have implications for our understanding of cosmology and of smaller scale processes during that epoch. Okay, so before I start talking about physics, I just want to say, so I was reading this book a couple years ago. It's a good book. I can recommend it. And so this is a thing that is near and dear to my heart. And I'm in particular talking to those of you, well, talking to everyone for different reasons. Those of you who are in hiring committees, I would strongly encourage you to think about the following fact. Although it may seem like people who are mean to other people and barrel over other people are often more effective, more productive, more efficient, the net impact that they have on their place of work is incredibly negative, because they make the people around them so much less productive. So if you're considering hiring someone that you think might be an asshole, I would think about that. And if you're not yet in the position of hiring people, you can think about who you choose to collaborate with. You can also think to yourself about not personally being an asshole. So I think that's something that we should all, when we're interacting with each other, don't be an asshole. Hey! This doesn't apply to me. You can give me as much crap as you want during this talk. That's fine. Okay, so today we're talking about sizes, shapes, and structures, kinematics. And so two reasons for me that these link back to the big picture of galaxy formation is first, they are intimately linked to the formation trajectory of galaxies. And second, they are really at the bedrock of accurate physical models of galaxy formation. Back in the day, when we were first starting to simulate galaxies, one of the ways we knew that we didn't have all the correct ingredients in our models is that everything was just a dense bulge. It was also too massive, but that's how we knew we needed feedback in our simulations. This is from a paper by Hannah Ubler, which I really like, from 2014, showing the impact of feedback, and Andre showed this earlier. He's also the expert here, not me, not a simulator. The impact of feedback on the morphology of galaxies, right? So if you have strong feedback, apparently you end up with these big puffy situations, but in the not quite as strong feedback, you have much more extended disks. When there's less feedback, you have these dense bulges. So these observations of the structures, the kinematics, the sizes of galaxies all can place stronger constraints on the key kind of physical ingredients in our models of galaxy formation. The other thing is that galaxy structure is intimately linked to the formation trajectory of galaxies. So you've seen probably a lot of these different plots through the years. There's a bunch more that aren't even up here but I couldn't fit them with you still being able to read anything on them. The main point here is that what we have observed empirically is that it seems that once the high surface density center of a galaxy builds, that galaxy is most likely to quench. Why? We're not precisely sure. A lot of people have theories about that. But this is a quite strong empirical correlation. And so that tells us that the structures of galaxies are very closely tied to their star formation histories and their ability to grow stars in the future. So I think I'm gonna skip this next bit. Well, yeah, so yeah, we're gonna skip this next bit because I'm gonna be behind otherwise. So one of the reasons that we launched the James Webb Space Telescope, actually, I'm gonna just go back because I don't want you to see this yet. Okay, so so one of the reasons I was told that we launched the James Webb Space Telescope, this may or may not be true, but I'm going with it because it works for my purposes. So apparently when the initial Hubble images came down, these galaxies, they didn't look like, these high redshift galaxies didn't look like local galaxies at all, and that was apparently a surprise. We expected to see these, these spirals and ellipticals at earlier cosmic times, and instead, as one fairly famous astrophysicist describes them as, these galaxies are a fucking mess. And so that told us that that galaxies actually really strongly evolved through cosmic time. And so we needed to be able to look back to much earlier cosmic times if we were going to actually figure out how these things formed. So that is allegedly, in my world, the reason that we have James Webb. And so James Webb does two amazing things for us, right? It increases the sensitivity in the near infrared, and crucially, it also increases the spatial resolution by a lot. So you may or may not recognize this. Anyone know what this is? Of what? What's it an image of?
It's the sky.
It's the sky. You'll recognize it in a second. Yeah, baby, that smacks. Yeah, this is a really famous image, right? And you didn't even recognize it in Spitzer. Because not only are all of these little faint galaxies missing from the Spitzer image because we didn't have the sensitivity to detect them, they also, we don't resolve anything, right? Like, Spitzer's great and all, but like, we just see we can't see the structures of these things at all. They're just big fuzzy blobs. So really, James Webb gives us the ability to actually resolve these early galaxies and start to get an understanding of how they're forming. So, in this talk, we're gonna just plow through here. We're going to talk about what are the sizes of early galaxies in a limited way, because we already heard a lot about that. What are their shapes? We will just complement what has already been discussed. And what are the kinematics? So, this is a quiz. What are the sizes of early galaxies? Shout your answers. Yeah. Exactly. They're fucking small. Yeah, they're really small. There's a lot of different works that have shown this. They are really very small. And that's not surprising, right? The universe, for all the reasons like Andre suggested, yeah, the universe is smaller also. So great. Okay, so the caveat here, I thought Ariane was going to talk about this, but he didn't. The caveat here is that measuring these sizes that are like about the same size as the point spread function or even smaller really requires an exquisite knowledge of the PSF. So as we better characterize the PSF through time, hopefully, these measurements are subject to change somewhat. Okay, so we have, but the fact that these are really small sizes means that the physical properties, the inside of these galaxies, they're really high densities, as we heard about from Alice this morning and Dan. That really drives the physical conditions inside of these objects. So we heard a lot about the sizes already today. I wanted to add on one additional thing about the sizes of galaxies that is related to yesterday's discussion of the little red dots. So I'm sorry, I'm telling you the whole story here, and this is how it's going to be. We're doing personal interest today. When I first saw the James Webb Space Telescope images, the thing I was most struck by was, okay, so this is Hubble. I was looking for things that were not detected in Hubble. And the first thing I noticed was these big fatties, these big fat red discs, and I was just like, these are crazy. So my friend and colleague Rachel Bazanson and I went about trying to select these things and characterize them. So we came up with a color selection for them. And then, we had this color selection, and we were, and so we did, of course, the first thing you do if you have light is you want to actually measure the physical properties of galaxies. So we, started measuring their masses and redshifts. And one of these things was not like the others, and that is this puppy. It's small. It's not as nice looking as the big red discs, but it is a little red dot. So when we actually modeled the, the photo-Z's and the stellar masses, we were very surprised, right? This is the fiducial stellar mass and redshift of this thing was at a redshift of 9 and a stellar mass of 10 to the 11. And so, of course, our immediate thought was like, this thing's got to go to nature tomorrow. So, we sent it around to all our colleagues. People checked masses. Our colleague Eva Labbe found a couple of additional ones with a color selection. And so we had this, we got this thing ultimately into Nature, I think 2 days after that, not the next day. But they went through some iterations because, the 0 points and stuff and, lots of uncertainties with the star masses. But these are chunky boys. These are big boys. And we like big boys. So the thing is so we think these are fiducially very, when we first put these in, as we talked about yesterday, there's a lot of uncertainties here. But when we first put this paper in, we thought, these are really very massive galaxies at very early cosmic times. Of course, in order to actually say that, you really need spectroscopy, right? So we got a proposal through in cycle 2 to get spectra of these things. We kind of got spectra of them. So the observations were taken in February. And as you will see, it's a dumpster fire. So our spectra are terrible, which is really too bad because we were hoping for nice spectra, but there was a mirror tilt event. So we ended up getting, we only got about a quarter of the data, a quarter of the data is usable. But so we didn't get spectra of everything, and the spectra are really ratty and not very good. But they're enough, the spectra are enough to get redshifts, which is one of the key uncertainties in the interpretation of these objects. And the other is the emission line contributions. So one of the big suggestions at first is these things are completely emission line dominated. You're not actually seeing continuum. These objects are emission line dominated, and so that is what is driving these high fiducial stellar masses. So we got these spectra, and it turns out they're not catastrophic redshift failures. They are not emission line dominated in all the bands. Some of them have, emission lines contributing up to 40% in one band, but they're not completely emission line dominated. So these things really are red because of red continuum, largely. Now you can debate whether that is owing to red continuum from an AGN or red continuum from stars, but there is red continuum. So the redshifts went down somewhat. They're not catastrophic redshift failures, but they went down somewhat, and these stellar masses went down a little bit. But as Caitlin talked about yesterday, these stellar masses are very uncertain because we don't know how much this red continuum is contributed by AGN or stars. But one of the exciting things here is that we actually detect Balmer breaks in some of these objects. That was on the next slide I was looking at. So we detect these broad Balmer lines, and we detect Balmer breaks. This is actually from a totally separate paper by Bingji Wang, who found some Balmer breaks in the rubies, in the rubies survey, which I am not a part of. But so these objects have both broad Balmer lines and Balmer breaks. So one of the signatures we always think of as being, nail in the coffin for AGN is that something has a broad Balmer line and a narrow forbidden line. But there is plausibly a different interpretation. I'm not saying that it's right, but there is plausibly another interpretation for this. So we know that because these have Balmer breaks, we know that the continuum at rest frame 4,000 angstroms is dominated by stellar light, which means that if we measure a size at 4,000 angstroms, that represents the extent of the stellar body. It is not driven by a point source from an active galactic nucleus, right? So we know that when we're measuring these sizes, this is the starlight, because we have these Balmer breaks. So this is from a paper by Josephine Baggin, who is a graduate student at Yale. And basically, when she measured the sizes of these objects, they're incredibly compact. We're talking, these guys have masses somewhere. The masses are very uncertain, but they have masses somewhere between 10 to the 9 and 10 to the 11. And they have sizes of, 100 parsecs or less. So if you predict the velocity dispersion based on those stellar sizes, you actually come up with similar velocity dispersions to as measured in the Balmer lines. So it doesn't necessarily have to be AGN. I'm not saying there's not AGN. There's almost certainly AGN and stars in all of these objects. To Caitlin's point, if you have a bunch of gas that's going into sizes of 100 parsecs, you're almost certainly building a supermassive black hole and a bunch of stars. But the point here is that we can use sizes to potentially yield some physical insights into these types of objects. Okay, so we know that all these galaxies at early times are really little. So how do they grow in size to today, right? Galaxies are big today. They're big boys. So one way we can do this, this is the efficient and painful way to do this. It's what I did for my thesis. You can take a grism, right, and you can so the thing you need to figure out how galaxies are growing is you need a measurement of the continuum, the stellar continuum, which maps where the stars are at the time of observation, and then you want to map the star formation to tell you how it's growing and where it's growing. So you can get both of these things from a grism survey, right? That gives you spatially resolved emission line maps. This is, it's rough out there, but it's a powerful tool, even if you end up looking at a lot of noise for your entire PhD thesis. But this was done to really, really interesting effect recently by a postdoc, Jessalyn Matharu. She used the FRESCO survey, which is a grism survey, to look at how galaxies are growing after the epoch of reionization. So she found that just like at lower redshift, galaxies are kind of growing inside out. The physical mechanism there is, of course, not clear because it's not clear, it seems unlikely that you have disks that are just like gradually getting larger in size, and more likely that you have, individual clumps and interactions bringing, and star formation that is preferentially at larger radii. You would need higher signal to noise individual maps in order to determine that, potentially. And one potential way to do that might be instead of using a grism, to use medium bands. So you can figure out where the star formation is either using spectra, right? Or in principle, if you have medium bands, which are basically a low resolution spectrum, a busted spectrum, if you have a very high equivalent width emission line that is in a medium band filter and then two broadband filters on either side, you can essentially probe where the continuum is versus where the emission line is. So there's been a couple programs now with JWST, both cycle 1 and cycle 2, that have done this. There's one by Christina Williams, one by Ren Cease. And so in principle, you can use this method to map the line emission. It hasn't been done a lot yet, interestingly, which leads me to believe it's harder than it seems like it's going to be. I did need to use this for my most recent paper, and you actually can quite effectively get an emission line map, which is this. But that will hopefully get used more as we run out of low-hanging fruit with JWST. So I'm low on time, huh? Oh yeah, I got 5 minutes. Okay, we're gonna skip this and just put this in you guys will have this in the summary. There's been a large diversity of morphologies at high redshift measured in a bunch of different ways. You know, we heard about this earlier with galaxies going bananas. So let's just say there's diversity of fruits at high redshift. Great. Okay, in addition to a diversity of fruits at a high redshift, you know, there's been a couple surprising things that have come out of my research group on this, and so I wanted to just quick touch on those. The first is that we found aliens, so that was cool. I'm kidding. So we found these ultra-flattened red objects, and we were jerks and decided to call them UFOs just for funsies. So we found these UFOs in JWST. So these were, to me, the thing that was most striking in the initial data. And so this is an HST image. This is a JWST image. And you can see this enormous red object. It does kind of look like an alien spaceship, doesn't it? Like a flying saucer. Yeah. So and it turns out there's a ton of these. So we initially thought, so we knew there's these HST dark galaxies, right? There's all of these objects that are, you know, too dusty or red for some other reason to be detected by Hubble. But the thing I was expecting for these things is that they would be very compact, right? Because if you want to have a high dust column in order to attenuate light, you would expect an object to be compact. I didn't expect these big extended disks. But we couldn't resolve these things before JWST. This was really something we could detect them with IRAC, but we couldn't resolve them. So these things were surprising for two reasons. Primarily, this is from a paper by my graduate student, Justice Gibson, who's graduating this year. It's my first grad student to graduate. Okay, so hopefully, fingers crossed. Okay, so we expected these things to be centrally concentrated in order to get these high dust columns. And instead what we see is they're basically exponentials. So these things have disk-like distributions. And the other thing is we expected these massive star-forming dusty galaxies to have high projected axis ratios, these kind of spheroidal objects. And instead, they have these really low projected axis ratios. So these are really elongated objects. They're likely, because of their masses, to be disky, but there's also some indication that they may be actually physically elongated, like prolate or something. So coming back to this slide I showed at the beginning, this galaxy, how the formation of galaxy structure is linked to the star formation history of galaxies. So, you know, we think that, you know, we have this empirical relation showing that once the high surface density center of a galaxy, its bulge forms, the galaxy quenches. But the question is, how and when did that bulge form? If you just see disks, blue disks, and then dead red bulges, like, what gives? So, like, how did that thing come to be? So, of course, the answer is that the rest frame near infrared. So in the rest frame optical, all of these star-forming galaxies are disk-dominated. In the rest frame near infrared, when we can look at these things and actually resolve them with James Webb, they have much more prominent bulges. So you can look at the profiles, the radial surface brightness profiles of these objects of quiescent galaxies in red, star-forming galaxies in blue. In 150, which is about the wavelength we had with HST, The quiescent galaxies are much more centrally peaked. As soon as we can look at them with James Webb, they have nearly identical central surface brightness profiles. You can see this also. This is by my student Chloe. This is going to be posted in the archive hopefully next week, which is cut the referee report. When you look at the central flux density, they're almost identical in the star-forming and quiescent galaxies. So what this is telling us is that you don't need some big dramatic event during quenching to transform galaxies from disky to spheroidal. They already built their bulges while they're star-forming. Okay, in the last -1 minute, we're going to talk about kinematics. Previous work suggests that there should be not very many disks at high redshift. The reason that there has not been that many measurements of this so far is because this is hard. We went from easiest to hardest, from sizes to shapes to kinematics. Kinematics are hard. You can measure kinematics in a couple different ways. You can use an IFU. That's the straightforward and expensive route. Takes a couple hours a pop. You're just not, unless you build an instrument, you're not getting that kind of time. So you can use slit spectroscopy. That is efficient. It is hard to interpret. Same with Grism spectroscopy. And maybe the best of both worlds, we're going to hear next, Susan. So the couple kinematic results so far that I know about this is from Anna de Graaf with using slit spectroscopy and doing dynamical modeling with some low-mass galaxies and jades. She finds a mix of rotation and dispersion-dominated objects, and these things are highly dark matter dominated, like a factor of 40 dynamical masses larger than their stellar masses. So this is much different than existing observations. I used the Grism to do kinematics because I'm a masochist. And so it actually turns out, though, that you can do this. And it's pretty cool. And it might actually be a kind of powerful way to get kinematics for large samples of galaxies. So what I found this incredibly striking, similar to Alice's object that she talked about earlier today, this massive, enormous rotating galaxy at a redshift of 5.3. So this thing is huge. It has a rotation velocity of like 300 kilometers a second at a redshift of 5. So it's also strongly dark matter dominated. And so, similar to some of the other trends that we've been seeing, this is evidence that galaxies, we have massive mature galaxies at early cosmic times. So just like when people give talks about the sun, I fall asleep because I'm like, I don't care. This is so boring. I don't care. So in case this is how you're feeling, because you don't like resolved information about galaxies, I will tell you one reason that you should care. And that is that integrated measurements, even if you only care about integrated measurements, they might be very, very wrong if you're not accounting for spatial variation in the mass-to-light ratios. This is a paper by Clara Jimenez Arteaga, and she basically finds that if you don't account for this spatial variation, you might miss up to 90% of the stellar mass in galaxies. So I'm just going to leave a blank conclusion slide here and take questions.
Thanks, Erica. We'll start with Nick.
Just a small clarification. So you're saying that dark matter dominated, but the pouch of the Milky Way is not dark matter dominated, right? The pouch of the Milky Way is entirely dominated by baryons. So you're saying they're not like our pouch. Essentially, these things.
In Anna's paper, or in?
Well, what dark matter dominated? So what do you mean as dark matter dominated here?
Oh, so I mean when you measure the dynamical masses of these things out to about the effective radius, the dynamical masses are a factor of 40 larger than the stellar masses. Is that what you're asking? Maybe I can talk to you.
They're very different from the pouch.
Correct. Yes, very different. And that is probably an evolutionary stage thing. So, yeah.
Yeah. Hi, thanks. I have a question about the very red and extended disks.
Yeah.
So I'm trying to see if that could be connected to the little red dots in any way. So I was wondering if, let's say let's assume they are disks. Then if you assume a three-dimensional mass profile that will be projected as a surface profile in 2D, and then you deproject it and then reproject it in phase-on direction, supposedly the disk component, at least in the outskirts, would get dimmer because you're viewing it phase-on. So if you observe it in a phase-on direction, then would we end up detecting only the central part, or also the bigger outskirts extended disks? This is basically the questions that Viraj and I would get, like for Proly Galaxies. So I was wondering if it also applies to these extended disks.
Yeah, totally. Great question. Yeah, so it's a great question. These things are whoppingly bright, like really, really, really bright. And they also have Sirsic indices of about 1. So as you can tell, like the centers aren't like dramatically brighter than the outskirts. The other thing is that actually, I was going to make this point and totally forgot. Interestingly, size can actually be a reasonably good way, because these low redshift things are so small. You can actually basically use the size to determine if something's high or low redshift, right? So these things are big. And so actually, when we cut based on size to get these things out, basically the thing it effectively did was cut all of the high redshift objects out. So, it's a great question, but I think these things are definitely like separate phenomena.
Yeah, thanks. Great talk, really interesting sources. When I look at these red disks, just putting on my millimeter galaxy person hat, I always have to ask, what cold, dust, and gas constraints exist for these, because, particularly in the cases where you say you're dark matter dominated, you look at a typical submillimeter galaxy that is very red like this, and the cold gas mass is a factor of 10 larger than the stellar mass. So I'm wondering, is there a statistical constraint from the cold gas in these sources?
Yeah, so these guys, so most of these, like, I don't have the plot in here, but I should, are, most of these guys are somewhat less massive and less star-forming than the SMGs are. But interestingly, I looked back at all of these, at a bunch of these SMG papers that do resolve the dust, and a lot of them have these really low projected axis ratio distributions, and they're not like super commented on in there, but like, so this was definitely detected in like these ALMA studies. But yeah, it's an interesting, but it's a little hard to figure out what to make of it. It's also actually kind of hard to model these things because, unless you make some weird assumptions about, what the inclination is, like the best fits are often like prolate, which honestly just like doesn't make a lot of sense for something that's massive. But but these guys are also like a little less extreme than the SMGs. Yeah. Okay.
That's a really outstanding talk. I really want to compliment you for that.
Thank you.
I have a question. You said several times growing inside out. Mm-hmm. And are you familiar with Mary Fowler in the geophysics from the UK? Because she's been looking at things going inside out from a gravitational point of view. So did Johnny Van Neumann, but he died back in the 50s, but he was fascinated in that too. So have you thought much more about that with your theoretical colleagues?
Yeah. So, I think to some extent, and it has been pointed out to me before that saying something grows inside out is like inane, but, I still say it anyway, because, of course, as the universe is growing, things, objects are growing larger in size, and so you're going to preferentially add mass to the outside. But it's a good point to think about how that might relate to other areas and how things grow in other regions of parameter space.
Yeah, hi, Eric.
Hi, Verda.
So, about these little red dots with broad dimension lines and Balmer breaks, for which you derive very high mass and very compact systems. Now, that's the case if the Balmer break is stellar in origin. However, as we said multiple times yesterday, many, if not most, of these little red dots have absorption in H alpha and H beta, which simply, without doing any postulation or any modeling, simply by atomic physics, must also have a Balmer break associated with it. So it may well be that these Balmer breaks have nothing to do with stars, are simply due to dense gas absorption, in which case you don't have any, constraints on the compactness and the mass of stellar population. So I wonder whether you have looked into that.
I have to be fully honest with you right now. I wasn't in the room for that part of the discussion yesterday, so I'm going to have to ask you about that afterwards. I don't know what you're talking about. So yeah, I'll have to talk to you later. Sorry.
Just to support Roberto's point, for the Bingji Wang sources, all three of them show strong Balmer absorption and Balmer breaks, which could, it's three objects, but.
Hi, Erica. Very nice talk. So going back to very, very compact, very massive galaxies, if you take, like you said, 100 parsec and 10 to the 10, 10 to 11 solar masses objects, and you assume a normal standard density profile, you get a core density that is 10, 20 times that necessary for runaway collisions between stars. So do you think that it's even possible to have stable stellar systems like that, or are we missing something?
It's a really good point. Hadn't thought about that. I'll need to think more about that. It's a good point. You're just getting stumped all day today. Love this for me. Okay.
You used a term that I haven't heard before. I apologize for my ignorance. Something about runaway or redshift or impossible redshift or something. Disastrous redshift.
Catastrophic.
Oh, catastrophic.
Oh, yeah.
What is that?
Oh, it's deeply unexciting. It just means that the redshift that you ultimately get from spectroscopy is further from the redshift that you infer from photometry than the error budget. So it just means that you're not getting the redshift totally wrong. Yeah, not very exciting. Yeah, sorry. I wish that was a more exciting term.
Thanks, Erica. I also want to echo Fabio's point that it seems like, I was going to ask you if you had calculated the stellar densities for the sources in the Baggin paper, because it seems like for most of the little red dots that we have, the high masses, if you assume they're continuing this solely from stellar, their high masses tend to have these absurdly high stellar densities that, as Fabio said, run into all kinds of issues. The other question I was going to ask was just regarding the narrow forbidden lines in these things. If the widths of the lines were only due to dynamics, then you start running into issues with why the forbidden lines are not also broad. And I know, in AGN, that happens because the densities are too high to have them present in the broadline region. But in these sources, it seems like I know in the Baggin paper it stated that potentially the densities are just that high, but then you have to then invoke another region of O3 emission that's more extended in this thing that is supposedly really, really compact to begin with. So I don't know if your thoughts on that.
Yeah, I think we are hoping with when we actually get the real spectra that aren't shitty, that we will be able to actually measure the width of the line spatially. So then we'll know the answer. Because I don't think it's at all impossible that you have O3 at larger radii, right? But you would need to measure it and test it to see if that's actually what's happening. Yeah, it's a good point.
So towards the end, you mentioned that if you didn't account for galaxies being clumpy, you would miss 90% of mass or light. I don't remember. Can you just say a little more about what you meant by that? If you don't account for it properly? Yes, that's the one.
Yeah, so basically, so Clara, did spatial resolved SED modeling of some of these galaxies. I think these are from SMAX, maybe. And when she did the resolved modeling, she got these, stellar masses that were a factor of 10 higher than the integrated measurements.
It's about the stellar mass modeling, not about the photometry or something.
Yeah, it's about outshining effectively.
Resolved.
Yeah. Yeah, exactly. And so you're still, you still don't fully obviously deal with outshining because but you're probably getting closer. But this, I think to me, one of the interesting things here is that if this is the common effect, we might, everyone's going to tell me we're overestimating the stellar masses, and that's probably true also. But we also might be underestimating the stellar masses. Consider that.
Susan, can you go set up, and we'll do one more from.
It should be pretty straightforward. It's cool to see the species for these sources, and while they're not catastrophic, like they are, like as you said yesterday to me, like they're like delta spec of like 1. What like as a person who thinks about photosets, like do you know what happened there? Like what was causing the photometric redshifts to be like 9 when they're actually 6, or sorry 8 when they're 6, or 7 when they're 6? Like what should we be worried about all the LRD photoses for this?
I mean, I think, and you are intimately familiar with this issue. It was a template mismatch. There weren't templates that had red enough continua with strong enough emission lengths. Yeah. So, I think, if the correct templates are included in the fitting, which I think they typically now are, hopefully that gets you there. But yeah, we didn't have red enough continue.
Awesome. Let's thank Erica one more time.